All right, so we're going to talk about dot product, or also known as the scalar product, and then we're going to talk about finding the moment of a force vector about an axis. All right, let's get this. Oh, I did it right. Ah, sorry about that. So there we have it. First, let us discuss the scalar product, or more commonly referred to as the dot product. I'm sure you've all seen this before, at least I hope you have. If not, we'll do a very brief review here. Dot product. Some books refer to this as the dot product, some as the scalar product. The dot product is probably the more universal one. But the B reactor mechanics book does use the term scalar product, but that's okay. Scalar product. What does this mean? The dot product or the scalar product? Well, the dot product represents the projection of one vector onto another vector. So remember in the previous example, we could interpret these graphically. Remember in the previous discussion over cross product, we had a discussion over what it meant, like using the right-hand rule and things like that. That was sort of a graphical interpretation of the cross product. The graphical interpretation of the dot product would be the projection of one vector onto another. Is the projection of one vector onto another. What do I mean by this? Let me show you. So let's say I have vector A. This is going to be a quick and dirty graphical interpretation of dot products. And vector B. Well, if I project this one down to here, this length here would be A dot B. This length here would be A dot B. So that is one way to interpret a dot product, at least in terms of graphically. So that's how you can interpret a dot product graphically. But we also want to go over a few more other things about dot products. So let us look at that. Well, let's see. What else can we say? Well, what if we wanted to know the angle between them? Let's say we had this here, theta. Well, another property of dot products is that you can say, if I have A, you've probably seen this before, A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And this works not only in 2 dimensions, but in 3 dimensions. So yes, in many cases you can calculate in many cases you can quite easily calculate a 2-dimensional angle between something without using a dot product. But often if you have 3-dimensional vectors, it can be very difficult. It can be very a large cumbrance to try to calculate the angle between vectors in a 3-dimensional system without using a dot product. So, all right, questions on that? Okay, fairly straightforward, very basic theory. Now, let's look at actually calculating the dot product. So this is fairly straightforward. if I have A, let's look at these in terms of their rectangular components. If this is components, if vector A has components AX I plus AY J plus AZ K, and B has components BX I plus BY J plus BZ K, A dot B is simply equal to AX times BX plus AY times BY plus AZ times BZ. Note, result will not be a vector, but a scalar, a single number. Will not be a vector, but a scalar. Honestly, dot products are generally far easier to calculate than cross products. A fairly simple thing. Okay, so questions on that. In case this isn't clear, I'm going to work through a very simple example calculating a dot product of two vectors. All right, questions on that? You got that? Okay. So let's do a trivial example calculating dot product. Dot product example. So let us say vector A is equal to 3 meters, comma, negative 2 meters, comma, 1 meter. And vector B, again, I'm just sort of pulling numbers out of the air, is equal to negative 4 meters, comma, 6 meters, comma, negative 3 meters. All right, then A dot B. Note, it is commutative. It does not matter which order you take these in. The cross product actually does matter which order you take them in. If you take them in the opposite order, you'll get the same magnitude but the opposite sign, positive or negative. Here, though, on dot product, you'll actually end up with the exact same result, regardless of which one you take. Okay, so this will be 3 times negative 4 plus negative 2 times 6 plus 1 times negative 3. 3 times negative 4 plus negative 2 times 6 plus 1 times negative 3. This would be negative 12 minus 12 minus 3, and that would all come to negative 27 if I'm mathing correctly, and I believe meters squared. Although the units are somewhat unimportant here. All right, questions on this? Fairly straightforward dot product. So really, hopefully, dot products aren't too bad. Now, I would like to introduce also something called the mixed triple product, which really isn't so bad. It's just combining dot products and cross products together. This is sometimes called the mixed triple product, but it's really just if you have vectors S, P, and Q, the mixed triple product would be S dot P cross Q. And the order here does matter. So you can read more in the book about the theory behind that. I don't want to spend, I don't like really spending a whole lot of time discussing that, but it really just basically, we're going to use this to calculate the moment about an axis. We're going to use this to calculate the moment about an axis. Huh? It's not a volume, no. Well, actually, yes, it is the volume of a parallelogram. Yes, I believe so. But I need to read up on that. It may very well may be. Okay. May have units like that. Okay. Now, let us discuss this. So, um, let us discuss, did y'all get that? Okay. Let us discuss moments about an axis. Maybe I'll actually write this as the moment of a force about an axis. Moment of a force vector about an axis. Moment of a force vector about an axis. Moment of a force vector about an axis. So let's say I have this. How will we do this? Well, what we're going to say is we're going to have, let me write the formula first, and then I'll actually describe what this is. Moment is going to be equal to lambda dot m, or b, I should say, lambda. Let me just write this down, and I'll actually get into describing what all this nonsense means. Lambda dot RAB cross F. So we need to actually figure out what all this nonsense is. So look here. So in general, let us say I have an axis that I want to take the moment about. Say I want to take a moment about this axis. Say I have an axis, from an axis, maybe this is point A here, maybe this is point C, and then out here somewhere, I have B. I like doing my forces in red if I can. I have a force vector here, force F. R is from A to B, RAB. And then lambda, you know, to be consistent, let me call this lambda AC. Actually, let me just finish. This is lambda AC, or just lambda, either one is fine. Lambda AC. So basically what this is F is the force vector. RAB is going to be the vector from any point on the axis, point not of, on, any point on axis to any point along F's line of action. On F's line of action. And lambda AC would be the unit vector of the axis that we're considering. Of axis we are considering. So, if I had just if we have learned so far how to calculate the moments produced by this force about point A. Point A is just anywhere along the axis that we're considering. So here, you know how to take the moment of this force about this point. We have looked at this many times before, or not many times, we've looked at it since last week. Well, we've looked at it a few times. You should hopefully know how to do that by now. So this is you know how to calculate the moment of this force about this point. So the result of that will be a vector, a moment vector in the I, J, K direction. So you're going to end up with some vector m, like here, or something like that. But we don't want all of that vector. We only want the portion of that along lambda AC. So we're getting the entire moment vector, this moment vector here. And you know what? For consistency, let me call this moment A. Because that's just consistent with what the book was using B. I'm going to use A with what I set up here already. All you really need to know is that it is lambda dot r cross f, where lambda is the unit vector of the axis we're taking it about. R is the actual vector, not the unit vector, but the vector from a point on the axis to the point where the force acts through, and F is the force vector. Yes?
It kind of looks that way, but F doesn't have to be parallel to the axis.
The question is, it kind of looks that F is parallel to the axis. Does that have to be that way? No, absolutely not. In fact, you know what, just for fun, just to be absolutely clear that we're not looking for a vector that's parallel to the axis, I'm going to purposely draw something that will be way off the axis to eliminate any ambiguity. So I'm just going to do something like that. That better? Okay. All right. Questions on that? That's the theory anyway, and I can work through some examples. So again, the moment about a point will give you a vector. That's the moment vector, a I, J, K component of the moment about point A that this force produces. But then we're saying I only want the moment about one axis and one axis alone. In other words, it's kind of like saying, okay, imagine I have a door. Say I have a door. I have to draw a doorish looking thing. And a door has an axis here, right? It has an axis on its side. What happens if I come along and apply a force at a weird angle? Not, you normally apply a force to a door like at this angle. But what if I do something really weird and I apply a force like that? See, in that case, if I wanted to calculate how fast the door will rotate, I wouldn't want to use the entire moment. I wouldn't want to use the entire moment this thing generates at about a given point. I would want to calculate only the moment that is in line with this axis, because only that is actually going to cause the door to rotate. The rest goes into applying forces to the door and such, but it goes into applying forces maybe toward the hinge or something like that, but it's not going to actually accelerate the door in any manner. All right, other questions? That kind of makes sense? Do you get a feel for what we're kind of doing here? Okay, hopefully. Okay, so actually no, yeah. So I'm going to use the formula M, and notice I'm not using a vector sign here, is going to be equal to lambda dot r cross f. That is sort of our guiding light here. So let us consider an arbitrary system. Let's say I have an XYZ system. Now, for simplicity, I'm going to have the axis pass through the origin. That's just going to make the math a little bit easier. So let's say I have an axis here. Maybe I have this point. I used point C there, so I'll do that as well. So let's say I have an axis here, C, O, and let's say C has coordinates, negative 2 meters, comma, 1 meter, comma, negative 1 meter. This is a coordinate, not a vector. And then let us say I have a force out here. Let's see. I'm going to need a line of action of the force. So let's say I have somewhere on the x coordinate, I have point B here. And let's say point B has coordinates 5 meters, comma 0 meters, comma 1 meter. And then let us add a line of action for this force that passes through point O. Let's call this point D, which has coordinates, let's say 7 meters, comma, I don't know, let's say 3 meters, comma, negative 2 meters. And let's say F has a magnitude of 18 newtons. Okay? So I am tasked with finding the moment of this force about axis OC. Find the magnitude of this force of F, F's moment, I should say, F's moment about axis OC. Of F's moment about axis OC. Okay, so I know I need this, this, and this. So that's what I'm going to try to get. So first, let me get the force vector. Well, let's see. It's going to be, clearly, it's going to be 18 newtons times the unit vector along its line of action, unit vector BD. So that's going to be, well, let's see. First, I need vector BD. Actually, I don't like this over here. I know that vector BD, not unit vector BD, but just vector BD, equals, let's see, that's going to be 2 meters, comma 3 meters, comma negative 3 meters, right? 2 meters, 3 meters, negative 3 meters. And lambda BD, the unit vector along line BD, is going to be equal to, well, I can, that's all right. 2 meters, comma 3 meters, comma negative 3 meters over the square root of 2 squared plus 3 squared plus 3 squared. And that's going to come to, let's see, it's going to be an ugly unit vector, 2 comma 3 comma negative 3, and square root of 4 plus 9 plus 9. This over this. So I get lambda BD, let me put this down below, is equal to 0.426 meters, comma 0.640 meters, comma negative 0.640 meters. Any questions so far? This is all the kind of things we've done already before. So I'm going to try to squeeze as much as I can onto this one slide if possible. So we have this. Now, the force vector F is simply going to be 18 newtons times lambda BD, which will be 7.675 newtons, comma 11.51 newtons, comma negative 11.51 newtons. So that's the force vector. So we have this part here, then we need R. R is going to be, well, it's fairly straightforward. It's just the vector, again, from any point along the axis to any point that the force acts through. So we could use the one here, or we could use the one here. For simplicity, I'm just going to use the B here. Okay? R is going to be equal to 5 meters, comma 0 meters, comma 1 meter.
Can you say that again? Like, which ones could we have chosen?
You could have chose this one or this one. B or D, yes.
So this is okay. So this is R.
R it is basically OB.
Okay, ROB.
We can choose a vector from any point along the axis to any point along the force's line of action. Okay. So then I can say, let's see, lambda, oh man, this is going to be fun. Lambda OC is going to be, from O to C, is going to be negative 2 meters, comma 1 meter, comma negative 1 meter, over the square root of 2 squared plus 1 squared plus 1 squared, or the square root of 6, which comes to, let's see, negative 2, comma 1, comma negative 1, divided by the square root of 6. So lambda OC is negative 0.816, comma 0.408, comma negative 0.408. Okay, so let me just, oh, you know what? I'm going to give myself another slide here. Insert new slide. Give me a little more working space here. Okay, so let me just rewrite what I already have. So I know the force vector. The force vector, again, is 7.68 newtons, comma 11.51 newtons, comma negative 11.51 newtons. Our R vector from the axis to a point along the force's line of action is going to be this 501, 5 meters, comma 0 meters, comma 1 meter. And then the lambda is going to be equal to negative 0.816. Oh, that looks terrible. Negative 0.816, comma 0.408, comma negative 0.408. Like so. And now I need to calculate a, do you need me to run through the cross product calculation, or can I just take care of that really quick? Or do you want me to run through it? Or are you good with cross products? You're good with cross products? Okay. So let me just, I'll just let my calculator chew on the cross product really quickly. R cross F, because let me show you the whole formula here so you'll see what I'm doing. The formula I'm going to apply again is M is equal to lambda dot R cross F, like so. First, let's get R cross F. We know how to do cross product, so I'm going to be a little lazy and just throw this into my calculator. Let's see. Nope. Matrix, sector ops, cross product. Okay, R cross F. I get negative 11.51 Newton meters, comma 65.24 Newton meters, comma 57.56 Newton meters for R cross F, and then lambda dot R cross F is this dotted in, so it's this dotted into this, and again, I'm just going to be a little bit lazy. Do the.
Is it lambda of C? Is it lambda?
It's going to be the lambda of the axis. So it's going to be that, comma that. Oh, I selected dot. Just a second, math matrix. This, comma this. And I get exactly, or approximately, 12.53 Newton meters. So, let's look at this for a moment. The actual moment, the moment vector is the whole negative 11 point, so this is the answer here, 12.53 Newton meters. I just want to compare it to something. Negative 11.51 Newton meter I plus 65.24 Newton meter J plus 57.56 Newton meter K. What's the actual magnitude, the total moment of vector M? Well, it's going to be the square root of 11.51 squared plus 65.24 squared plus 57.56 squared, and that comes to about 11.51 squared plus 65.24 squared plus 57.56 squared, and that comes to 87.76 Newton meters. So you notice, about the axis that we are, this moment, at that point we were considering, was generating a total moment of 87.76 Newton meters. However, only a portion of that was actually about the axis we are considering. Only 12.53 Newton meters of that moment could be considered directed about that axis. So most of it was actually not about that axis. Most was in other directions. All right. Other question? Any questions on this? Be sure to read your book. It'll go over this in more detail, etc., etc. Okay. The cross product of the vector from here to here, from O to B, and the force vector here gave me the moment of the, actually, you know what? Let me label a force on here. Let me make clear where this force is here. Force F acts along this vector here. Force F acts along this vector. So the cross product gives us the moment of this force about this point. And then the dot product gives us takes that moment and tells us how much of it is directed along the axis that we're considering. Okay?
So you did your R cross F on your calculator, hand calculator?
Yeah, so
And then you saved that result and you applied lambda to it?
yes, I mean, I could easily do the dot product just writing it out, but I did the question was I got the dot product by just using my calculator. Yes, I did, just to save a little time.
I tried to do that on my calculator.
You probably can't with a hand calculator. You probably need to use a graphing calculator, but that's okay. Okay, but not on your exam. Okay, but you know how to calculate dot and cross product. We've gone over that many times. Okay, other questions? have a couple more examples I might work through, but let's move on. Okay. So you have this. Let's look at this one here. So this is 3.48 in the Beer Vector Mechanics book. Knowing that the tension in cable AC is 1,065 newtons, determine the moment about each of the coordinate axes of the force exerted on the plate at C. So this looks familiar. We've worked with a bit of this in previous things, in previous classes. So the moment in, let's see here. So we need to determine the, okay, so let's do that. So let's see, how might we do this? Well, we're going to have a force vector acting along line CA. I'm going to have a force vector acting along CA. This is the force vector. Then I'm going to end up finding the moment about this axis, the x-axis, the y-axis, and the z-axis. Okay. Now, remember, I need some vector r that goes from a point on an axis that we're taking the moment about to some point on the force's line of action. I'm going to choose to do the origin because that point is present in all three of the axes. That will allow me to use the same r for each of these axes. Just keep me from doing a bunch of work over again. So r, in this case, will go from O to C. R. So let me first get what I might call MO. So I'm first going to get MO, the moment about the origin, and that will have X, Y, Z components. But first, I'm going to need to find the force vector. Well, I can get R very quickly. That's fairly trivial. This is going to be, so let's see, R is going to be, that looks like 900 millimeters, or 0.9 meters. So 0.9 meters, comma, 0 meters, comma, 1280 meters. That's vector R. Oh, 1.28 meters, sorry. 1.28 meters. Is that right? Yes, 1.28 meters. Now, I need to get the vector from, I know we've calculated this previously, but that's okay. I know in a previous class we actually calculated this vector before, but that's okay, whatever.
How did you choose your R again?
How did I choose my R? The question was, how did I choose my R again? I chose my R. Remember, R is from any point on the axis that I want to take the moment about to any point along the line of action of the force. I could use the R from here to here. I could use the R from here to here, but I could only use this one for the x-axis problem, part of the problem, because that point B is only on the x-axis. Rather, I chose a vector from point O because that's going to pass through both the x, y, and z axes. Okay, so let me get RCA again. Okay, so this is going to be negative 0.9 meters, right? In the x, comma, 0.6 meters in the y, comma, negative 0.92 meters in the z. In the z, lambda CA is going to be equal to 0.9, comma, come on there, negative 0.9, comma 0.6, comma 0.92. All of this over the Pythagorean, 0.9 squared plus 0.6 squared plus 0.92 squared. And that comes to 0.9 comma 0.6 comma 0.92 divided by the square root of 0.9 squared plus 0.6 squared plus 0.92 squared. And we have a unit vector. Again, I know it can be very confusing in problems where you have two different unit vectors, but it is very important not to mix them up. We have one unit vector that we're only going to use to find the force vector, and then then we'll have other unit vectors actually describing the axes. So here, this comes to 0.9. Yes, but actually, wait a minute. Let me see. 0.92, is this 0.92? Yes, thank you. Yes, in the z. Yes, negative 0.92. Thank you. Let me adjust this really quick. Okay, and I get 0.634, comma 0.423, comma negative 0.648, like so. And that is the unit vector of this force. And then I can simply say, yes. Did I get mixed that one up as well? Oh man, I'm not transposing things properly today. Okay, it's Monday. So then that's just going to be a negative here. Yep, okay, thank you. So the force vector then is just going to be 1,065 newtons times lambda CA, which is 1,065 times all this, negative 0.634, comma 0.423, comma negative 0.648. And the force vector then is this times 1,065, and this is negative 675 newtons, comma 450 newtons, comma negative 690 newtons. And that is the force vector along that line. So let me find the moment next, because remember, let me find the moment vector next, I should say. The moment, not the moment vector, but the moment about an axis is going to be lambda of the axis dot r cross f, like we've seen before. So I want to get this, but this here, though, is just the moment vector about a point on the axis. So I want to get the moment vector. This is equal to r cross f, which is going to be equal to 0.9, comma 0, comma 1.28 crossed in to the force vector of negative 675, comma 450, comma negative 690. And again, I'm just going to let my calculator chug on this for simplicity, for brevity, I should say. Here, okay, negative, actually 0.9, comma 0, comma 1.28. Huh?
You can't use RCA in this?
I can't use RCA in this. RCA, let's see, CA. C2A. No, I can't use, wait a minute, why could I? No, but we already did use that. We already did use that. Let me think about this. Okay, we can't use RCA because we need to use vector OC. Let me say moment about O equals ROC times the moment vector of this force about point O is equal to the vector from O to C crossed into the force vector. Okay? And this is ROC. Okay, questions on that? Okay. Cross product of this and this. Okay, and I get negative 576 Newton meters, comma, negative 243 Newton meters, comma, 405 Newton meters. And some of you may be seeing where this is already going, but if not, that's okay. We're out of room here, so I'm going to give myself another slide again. So we have that, and then, okay. Okay. Y'all got this? Oh, anyone still copying this? You got this? Okay. So I know the moment, the overall moment vector about the origin is, again, negative 576 Newton meters, comma, negative 243 Newton meters, comma, 405 Newton meters. However, I am asked to find, must find moments about x, y, and z axis. X-axis, y-axis, z-axis. However, the lambda for the x-axis is fairly trivial. It's just I. It's just 1, 0, 0. The lambda for the y-axis is just j or 0, 1, 0. And lambda for the z-axis is just going to be equal to k, which is 0, 0, 1. And then, if, say, the moments about the x is going to be lambda x dotted into m naught, well, that is 1, 0, 0, dot negative 576, comma, negative 243, comma, 405. That is clearly simply going to be equal to the component of this, negative 576 Newton meters. That's mx, moment about the x-axis, and my, by the same logic, is going to be negative 2. Yes? No, because this is, by definition, unitless. Newton meters. Moments must always have units of Newton meters or foot kips or foot pounds or something like that. The question was, would this be Newton meters squared? 405 Newton meters. Like so. So this actually gets at what the, I like this because this actually gets at what the vector components of a moment actually mean. What this tells us is that the components of a moment are actually the moment, what the components of a moment are the moment you get when you take that moment about a certain axis. So, in other words, and we'll look at this more when we get into couples tomorrow, if you have a moment vector m, which means a moment about, say, just some arbitrary axis, it has a moment about the x-axis, mx. It has another component, my, about the y-axis. I should probably actually use probably shouldn't use the component sign, the vector sign for that. And it has a component about the z-axis. z, like so. All right, questions on that? Okay. Any other questions about anything from today, anything going on tomorrow, et cetera, et cetera? All right. With that, I think we'll cut it a little short today. I think I did have another example that I could work through, but I think it's very similar to what we just did. So I think that should work. If you need any assistance, I'll be doing office hours from about 2:30 to 3:30 today. It's a little bit different than normal. And then, let's see, so we'll have a lecture on couples tomorrow. Basically, we're finishing up chapter 3 tomorrow in the beer vector mechanics book. We're finishing up couples. Then the exam will be on Wednesday. It'll cover chapter 2 and 3 material. So basically everything you ever wanted to know about vectors. So if you have any questions, feel free to drop by or see me after class, et cetera, et cetera. That should do it. Try to take a crack at those problems tonight. And as always, thank you. Huh? Tomorrow's lecture will be on the test, yes.